Let us start with our next lecture, namely lecture 8, which is a continuation of our previous lecture on friction. And today in this lecture, we will be discussing continuing further with friction and its application. You can recall that last time when we were defining friction, it was said that friction is a distribution of force which tries to prevent motion, and if motion is already existing, then it tries to impede that motion, and it was due to the presence of asperities on the surface. We also discussed two types of friction, and mainly our emphasis was on dry friction or Coulomb friction. We discussed also the laws governing dry friction, and then we looked into some examples on friction. In most of those examples, we knew which way the direction of motion is likely to take place, or it was already taking place. So, the force of friction was applied in the opposite direction. When we discussed the equations of equilibrium, in most of the examples or problems we discussed, two equations of two equations of equilibrium were sufficient, namely sum of the forces in the x direction is equal to 0, sum of the forces in y direction was equal to 0. The third equation for plane forces for the two dimensional case, namely the sum of moments about an axis perpendicular to the plane of forces is equal to 0, was very rarely used, because we generally do not know a priori the direction of or the line of action of the normal reaction. In the end, we took up an example, namely the toppling or tipping of a crate, in which we could fix the direction, fix the point through which the normal reaction was passing, and then the equation of equilibrium, the third equation of equilibrium, namely sigma mz about that point, was taken to be 0. And now we will continue with few more examples. We will be discussing friction problems in which the direction of force is not known a priori. That is, we do not know in which direction the friction force will be acting. So, we have to make a judicious choice depending upon the circumstances of the problem. Let us look at this problem. Here is a box which is lying on an inclined plane. The slope of the inclined plane is also given. Now, a force of 450 Newton is trying to push the block up the incline. We have to decide whether this force will cause the motion of the block up the incline, or it will stay in equilibrium, or it will, in spite of applying this force, the box will slide down. So, we have to make a decision. So, we will examine various possibilities one by one and then come to a logical conclusion. First case we will consider that the block tends to move up the incline, that is going up. So, and we are considering the case of impending motion. The box is still in equilibrium, but a slight increase in the force can push the box upward. Okay. So, if you look at this problem, since the impending motion is upward, therefore, the force of friction, the static force of friction will be down the incline. So, that is why I have taken it in this direction. So, now the box is in equilibrium due to these forces. One is the weight is already given as 1350 newtons, which is vertically downward. So, you can see that it will be a weight of 1350 as we have already shown over here. This weight can be broken into or resolved into two components. One is in the normal direction and the other is in parallel to the incline. So, if we consider the local coordinates x parallel to the incline and y is perpendicular to the incline, then sum of the forces in the x direction is equal to 0, sum of the forces in the y direction is equal to 0. So, from that we can calculate from two equations, we can find out the two unknowns, namely the normal reaction required and the secondly the force of friction. The force of friction F, which is down the incline, comes out to be 360 newtons. Okay. That is the force required at the time of impending slip, that is it is about to go up the incline. Maximum force of friction which can be provided, because the coefficient of static friction is already given as 0.25. So, according to Coulomb's third law of friction, this is mu s times n. So, this will be equal to 0.25 into the normal reaction at 1080, and this comes out to be 270 newtons, which is less than the force of friction which is which comes into play at the instant of impending slip. Okay, that is the maximum force, frictional force which can come into play. It means that the system or the box cannot stay in equilibrium, because sufficient force of friction is not available. Hence, the box will slide down. Therefore, the block will not stay in equilibrium and it slides down the incline. That is the conclusion from case 1. Let us move to the second case then. Case 2, block moves down the incline. Okay. When the block is moving down the incline, then the force of friction will be up, and again taking x is parallel to the incline and y normal to the incline, again there is a 450 Newton force and a vertically downward load of 1350 is already there. Again sigma Fy is equal to 0, which will give me the normal reaction as 1080 as in the case 1. 1080 is incidentally 1350 into cosine of angle theta. Okay. So, once you get this, then let us say the force of friction F, which comes into play from the equilibrium consideration, is that 450 up the incline force of friction F, and then 1350 into sine of theta, which is 3 by 5. So, F comes out to be 216 newtons. So, this force of friction which is generated when it is about to slide down is equal to when it is sliding down is equal, that is 0.2 is the coefficient of dynamic friction, is 0.2 times the normal reaction, that is 1080. So, it is 216. So, when Fx is calculated with this value of F, it comes out to be minus 144 newtons. What does it mean? Positive x is in up the incline, so negative means down the incline. So, there is a net downward force of 144 newtons in case 2. So, the box will not only slide down, but it will slide down with a net force of 144 Newton. In dynamics, you will learn that this will be this will result in a downward acceleration. So, in the presence of 450 newtons upward force, up the incline force, the box will still slide down the incline with a force of 144 Newton, and hence if I divide by the mass of this box, then it will be equal to the acceleration of the box. So, in this problem we have seen that we examined various possibilities, because we did not know whether which way the force of friction is to act. We examined the two possibilities, force of friction downward and force of friction upward, and then came to a logical conclusion. Well, very often the friction concepts and the laws of friction are helpful in understanding some of the phenomena or some of the actions which we perform in our daily lives. And I will take up one or two simple examples, and you might be able to correlate these examples with your experience. Example 1 is pulling a wheel over a step. Suppose you are looking at this wheel which is rolling on this floor, and then suddenly it encounters a step. You can even take the example of an automobile which is to climb up a small brick or a stone, the wheel of the automobile. So, what happens at that instant? Sometimes you may find that the wheel starts slipping down, it's not able to climb, it slips. So, we want to examine what is the maximum height of the step x, so that the force P will roll a 25 kilogram wheel over the step without slipping at the corner A of the step. Okay. So, this wheel of diameter 0.3 meter is being pulled by force P, and the attempt is to raise the wheel up the step, that is it goes to the higher level, but without slipping. Okay. So, that is, we can allow only the state of impending slip. The coefficient of friction is static friction, of course, is given to be 0.3. Let us look at the free body of the wheel. Now, there is a force P, and we take the coordinate axis x in the horizontal direction, y is already given. There is a normal reaction from the ground N2, and at the corner, when the wheel is in touch with the corner, there is a normal reaction N1. Now, just at the instant of impending slip, the point in contact at the corner of this step, that is this point, will try to slip down, roll down, and therefore force of friction will be tangential upward at that point A. Okay. So, now let us consider the equilibrium. When the wheel is about to climb, it will leave contact with the ground. So, it means N2 will not be provided, and we will take N2 be equal to 0 at that instant. Now, let us take the moment of all the forces acting on the wheel about point O. So, from equilibrium consideration, sum of all the moments about point O is equal to 0. So, there are two forces, one force P and the other force, the force of friction over here, F you can say. So, these two forces will produce moment about point O. All other forces N1 will be passing through O, and hence it will not produce any moment. So, P is providing a clockwise moment, whereas force of friction is providing an anti-clockwise moment. So, you can see P into radius, the diameter of the wheel is 0.3, so radius is 0.15 is equal to 0.15 into mu times n, that is the force of friction at impending slip. So, cancelling out 0.15 on both sides, we get mu times n1 is equal to n2 is equal to P. So, this is the pulling force is equal to the force of friction at that instant, and then sigma Fx is equal to 0. What are the horizontal forces? There is a force P here and the horizontal components of n1 and the force of friction. So, sigma Fx is equal to 0 means mu n1, that is force of friction, times cosine theta minus n1 sin theta plus P is equal to 0. So, P comes out to be n1 into sin theta minus mu times cosine theta. From solving from equation 1 and 2, we get the final result as mu is equal to sin theta minus mu times cosine theta. Mu is known to us 0.3. So, we get to the final result that 0.3 is equal to sin theta minus 0.3 times cosine theta. Now, you can see from this equation that this equation is independent of the weight of the wheel, whether it is a light wheel or a heavy wheel, it does not matter. Well, square this both sides of the equation and rearrange the terms. You can come to this equation, which can be, after solving, will lead to, because it is a equation, quadratic equation in cosine theta. So, since cosine theta has to be less than or equal to 1, one solution will be realistic solution, other will not be. So, you will get cosine theta is equal to 0.834, which means that theta is equal to 33.4 degrees. So, the angle theta, that is this angle theta, is equal to 33.4 degrees, and from the geometry of the problem I can find out the height x, namely this will be equal to radius minus r cosine theta. So, the height x, capital X of the step is equal to the radius 0.15 into 1 minus cosine theta is already known 0.834. So, it is 0.0249 meters or 24.9 millimeters. So, this is the height of the step which the wheel can tackle without slipping down, and this height is independent of the weight, whether weight of the wheel, heavy wheel or a light wheel. Another day-to-day example which we can try to understand with the help of concepts of friction, and you might have seen very often that workers when they try to move a heavy box, they push a wedge underneath the box so that it is slightly raised up, and during that action what are various forces, which way the friction is likely to act, and so on and so forth, that phenomena we will try to understand. So, wedges are used to lift heavy boxes. So, let us look at this problem. There is a heavy box which is stopped and a wedge is used to push it between the box and the ground, so that the box gets slightly lifted up, and if I do not provide any support over here or a stopper here, during that pushing action the box will move, it will slide in this direction. To prevent that, we have a rigid block so that the box does not move, and let us examine the various forces which come into play in this section. So, So, this wedge has an angle of wedge equal to theta. Okay. So, let us examine the forces. This angle is very small. So, we will still consider the system to be almost horizontal. So, at that instant there will be these forces, reaction from the stopper F3, which is trying to prevent the motion of the box to the left. So, the reaction will be to the right, and from the ground there is a normal upward reaction at this corner, because otherwise the box is tilted, only one point is in touch with the ground at that instant. And then between the box and the wedge, well, you can see that this is the wedge and the box is the wedge is being tried to pushed into the box. So, there is a motion in this direction. So, there will be a equal and opposite force of friction, that is, this force is actually parallel to the surface of the wedge, something like this. So, this force upward this inclined surface, and then there is a friction force between wedge and the ground F2, normal reaction from the ground, normal reaction from the box onto the wedge. So, the wedge is subjected to 5 forces, 2 normal reactions, 2 forces of friction and 1 pushing force F, and the box is at this corner subjected to F1 and N1, equal and opposite to the corresponding forces on the wedge. All right. Now, we can examine, you can do it as an exercise yourself, we can examine the equilibrium of the wedge. All right. Also, we can examine the equilibrium of the box. So, you can easily see that there will be number of equations, namely the two equations from the equilibrium of the wedge, sigma Fx is equal to 0, sigma Fy is equal to 0. But when I come to the box, you will see, since the line of actions of the normals are normal reactions are known, so there will be 3 equations of equilibrium. So, total will be 5 equations, and we will have how many unknowns are there. We have the force of 2 forces of friction F1, F2, and the stopping force F3, and then you will have the reactions also. So, you can solve the equations of equilibrium to find out what are the various components of the reactions. Okay. Now, so far in all our friction analysis, we had contact surfaces which were plane, all right, that is box is on a level ground or etc., or wedge, etc. Now, each and every point of the plane surface has the same motion, whether it is actually when the bodies are actually slipping past each other, or whether it is a case of impending slip. So, the direction of motion of each and every point is same. So, the force of friction, which is opposite to the direction of motion or impending slip, is also same. So, that is a very simple or an easy situation where the magnitude and the direction of friction force, they are same for all the points. But in many cases, what happens is that the impending slip or actually happening slip is the direction of that slip is varying from point to point, and also the normal reaction may also vary from point to point. So, as a result of these two things, the force of friction is variable both in magnitude and direction on the entire contact plane, contact surface. So, how do we then analyze such problems? There is a simple technique. We will consider a small area, infinitesimal area, and we assume that on this small area the force of friction both in direction and magnitude is uniform, all right. And then we will integrate the force of friction over the entire contact area to get the net effect. And this whole procedure can be illustrated with the help of some examples. I will take up two examples to illustrate this fact, that is variable factor, the situation of variable force of friction, namely first example deals with thrust bearing and the second example with belt friction. Now, first I will take up thrust bearing. It is like this. Suppose there is a rotating shaft which is pushed against a rigid surface through a pad, a kind of friction pad, and the shaft is rotating. So, if I look at on the side view, I will see that this contact surface between pad and the rigid surface is a circular area whose diameter is d or radius is d by 2, okay. And if I consider a small element of this contact area subtending an angle of a small angle of d theta at the center of this surface, then we will assume that the direction of rotation is clockwise, then the motion is tangent at that point. That is, over here the direction of motion is like this, on the horizontal diameter it will be like this, on the vertical diameter it will be like this. So, at every point the direction of slip is different, and accordingly the force of dynamic friction which opposes the direction of slip will be also varying along the whole surface. I am depicting a small ring out of that surface, and if I see the topmost point of the ring, the direction of friction dF1 will be to the left horizontal. If I see the lowermost point, it will be to the right dF2. At these 2 points it will be upward, and at this point it will be downward. So, you can see that at every point direction of friction is changing. So, let us see how we can analyze this problem. First of all, we will assume that the thrust is, that is the pushing force between the pad and the rigid surface is uniformly distributed, all right. That is, each and every point receives the same pressure, okay, force per unit area. We consider a small contact patch subtending an angle d theta, as I illustrated earlier, at the center of the contact area. Then the pressure acting on this patch is the total force P, this total force P which is distributed over a uniform area on this area uniformly, then P divided by the area of the contact, that is pi d square by 4 into so this is the pressure acting on the patch on the entire area times the area of the infinitesimal patch. Well, r d theta is the arc length, dr is the radial length. So, arc length into radial length, that will be the area of the contact patch. So, this is the total normal reaction on this contact patch. Okay. Once again, if I show it, so this is the area r d theta into dr and times the pressure on this. Pressure is total force divided by the entire area. So that will give me the normal reaction acting perpendicular to this patch. And the force of friction, because the slip is already taking place, so dynamic coefficient of friction times the normal reaction will give me the force of friction acting on this patch, which is equal to mu d times p divided by pi d square by 4 into the area dr r d theta into dr. Okay. Now this force of friction is producing a moment at the axis of the shaft, that is namely the force times the moment arm. Moment arm is simply the radius. So this will be dm into 1 r is already there into moment arm. So r square mu d into rest of the expression is as such. So this is the moment generated by the force of friction acting on this small infinitesimal patch. Now if I integrate this infinitesimal, the contribution of the infinitesimal patch to the moment generated at the axis, so if I integrate it over the entire surface of the contact, that is theta is varying from 0 to 2 pi to cover the entire 360 degrees, and r is varying from the center to the outer periphery, which is at a distance d by 2 from the center. So the total torque which is generated by the friction force is integral of this expression from 0 to d by 2 over r and 0 to 2 pi over theta. Well, first of all, the theta integration is very easy. There is no theta term in the integrand. So this will give me 2 pi and then the r integration. So if you do this integration, I will get P, that is total thrust, times the diameter of the contact pad times the dynamic coefficient of friction divided by 3. Okay. So very simple expression, that is the torque due to friction, frictional torque is equal to the thrust times diameter times the dynamic coefficient of friction divided by 3. Well, this problem we did on the assumption that the pressure between the contact pad and the rigid surface is uniform. That is quite justified when the surfaces are new, that is there is no wear and tear of the pad. But after some time, after some usage, wear and tear has taken place, the pad is no longer exactly flat, it may have worn out from the edges and less wearing out at the center. So let us assume that the pressure, instead of being uniformly distributed, is distributed in such a way that more pressure as we go away from the center linearly, less pressure as we go away from the center linearly, that is P is proportional to 1 by R. Okay. Or introducing a constant of proportionality, P is equal to some A constant of proportionality divided by R. So again, of course at center it is very large pressure, infinite, theoretically speaking infinite pressure, but what we want to say is that pressure is decreasing as we are going away further and further from the center. All right. First of all, what is the total thrust corresponding to such a pressure? Again, integration r dr into d theta is the small infinite area of the small patch times the pressure. When integrated, give me the total thrust, and carrying out this integration, we can easily find that the total thrust is equal to 2 pi a into d by 2. and from there, since P is known, the total thrust is known, we can find out A is equal to P total thrust divided by pi times D. Okay. Once we have got the pressure, rest of the analysis is exactly same as in the previous case, that is uniform distribution of pressure. So, dN, that is the normal reaction on an infinitesimal patch, is equal to P times the area of the patch, and this P is already found out. And so, we substitute it. Again we apply the coefficient of dynamic friction, and we get the force of friction on this infinitesimal patch, and then again we take the moment arm as the radius of the that is radial distance of the patch, and then we integrate it to get the total torque friction torque transmitted. Okay. So, this integration is exactly on the same lines, and we will get, after integrating and putting the limits, we will get that this friction torque is equal to mu d times P times d over 4. In the case of uniform distribution, we had in the denominator 3. In the case of linear distribution, maximum at the center, minimum at the edges, we get 1 by 4. So, it means that the torque carrying or torque transmitting capacity of a worn out pad is less than that of the new pad, which is obvious also, but here is a full fledged explanation based upon laws of friction. Okay. Well, in some problems conical thrust bearings are also used. Instead of a flat surface of contact, we have a conical surface. Well, again the pressure will be normal to the conical surface, that is the slant surface, and again you can consider a ring of contact, and you can then find out what is the force of friction around that, and what is the normal reaction, and what will ultimately what is the contribution to the torque, because you know the moment arm, namely the radius at that point. So, again integrating over the entire slant surface of the cone, we can find out the total torque transmitted for the conical thrust bearing. Now, we come to a very important application of friction, namely belt friction. Well, you must have gone to workshop or some factory where several lathe machines or other workshop machinery is being driven from an overhead shaft with the help of belts. Or you can look under the bonnet of your car, you will find that there are 2 or 3 pulleys which are driven by the power from the engine, and these pulleys are needed to drive the dynamo or the alternator of your automobile, cooling system, and other components of your car. So, what is being done is that the power or useful mechanical work is being transmitted from the point where it is being produced or generated to several different locations with the help of belts and pulleys or drums. Okay. So, a schematic diagram of this arrangement is that here is a pulley or a drum of radius r, and a flexible but taut, that is in tension, a taut belt or a rope is going over this drum. It is in contact with the drum over a part of the drum, and the angle up to which it is in contact, this angle is called the angle of wrap. So, beta is the angle of wrap, that is the angle between the normal where the belt leaves off tangentially, it leaves off here as well as over here. These are the 2 points. So, the angle between these 2 points is the angle of wrap. Let us say the belt is rotating clockwise with a angular speed of omega radians per second, although we will not be going into the dynamics of it, but we will examine what are various forces, and we will assume that the belt is not slipping as yet. Okay. So, let us see how we can analyze the forces and torque transmitted. Remember, the tension on one side of the belt is T1, on the other side is T2, and if the impending slip is to take place in the clockwise direction, then T1 will be greater than T2, that is belt will be trying to slip like in this direction. Let us look at a small segment of the belt. It is in contact with this is the drum surface. So, this you can say drum or pulley, and in this with the drum is in contact with the belt. We are considering only a small part of the angle of wrap, namely the angle subtended at the center of the drum is d theta. Well, if I consider the center point of this, and let us say this is this center point of this contact d theta. So, half of it is d theta by 2 on the left side and d theta by 2 in the right side. The belt is having the tangent. So, the force of tension on one side will be T, and on the other side it will be T plus delta T, because the force is varying throughout the belt from T2 to T1. So, the variation on this small angle is from T to T plus delta T, and this is tangential at this point. T plus delta T is tangent at this point and T is tangent at this point. So, you can say point A. So, T is tangent at point A and T plus dt is tangent at point B. Okay. So, and if we extrapolate this tangent back, so you can see that this will make an angle d theta by 2 and a equal angle d theta by 2 on the other side. Consider the component of forces in the normal direction and the tangent direction at the midpoint O dash. Okay. So, if we do so, let us see, consider the, and then we examine the equilibrium and we consider the case when the slip is just about to take place, that is at the instant of impending slip. So, sum of all the forces in the tangential direction, T direction, that is in this direction, horizontal direction, is equal to T cosine d theta by 2, okay, that is the horizontal component of the right hand left hand force, tension force, and this is T plus delta T cosine d theta by 2, that is the horizontal component or tangential component of the right hand force, minus the force of friction. See, the slip is going to take place in this direction. So, the force of friction will be opposing that. So, it will be towards left, and this is equal to mu s, that is static coefficient of friction, times the normal reaction dN, right. So, you have once again this component of force, you take the horizontal component, this force take again the horizontal component, and you get the net force equal to 0, that is T minus T cosine d theta by 2, T plus dt cosine d theta by 2 minus mu s dN is equal to 0. Now, you come to the normal components, sigma Fn is equal to 0. Again the normal components, well, this will have a normal component upward, this will also have a normal component upward, and then there is a normal reaction. So, you will have this will be normal downward and normal upward. So, you will have minus T sin d theta by 2 minus T plus dt sin d theta. These are the two downward normal components of tension, and this is the normal reaction component upward. This is equal to 0. Now, these two equations can be simplified. Remember that the angle d theta is very small. So, d theta by 2 is also very small. So, for very small angles, you remember from your trigonometry, that is cosine of theta is equal to very close to 1 when theta is very small. Similarly, sine of theta is very close to theta itself when expressed in radians. So, when theta is small. So, it means cosine of d theta by 2 is replaced by 1. Similarly, over here sin d theta by 2 will be replaced by simply d theta by 2, and similarly d theta by 2 over here. So, from the first equation you will have minus t and plus t cancelling out. So, dt is equal to mu s into dN. So, the first equation simplifies to this simple statement, dt is equal to mu s dA, and the second is slightly requires little more attention, minus t d theta by 2, and then there is again minus t d theta by 2. So, it will be minus t d theta, and second will be dt times d theta by 2 plus dN is equal to 0. Now, the second term, if you look at it, there is an infinitesimal term dt and also d theta by 2, which is also very small. Okay. So, these two are very small quantities, and their product will be very small, extremely. So, these are higher order infinitesimals. So, in the limit, suppose I let d theta go to very small 0. So, this term will be going to 0 much faster. So, I can neglect this term because second order terms infinitesimals will be reducing much faster. Okay. So, it means second term can be neglected in comparison to first and the third term, and then the equation reduces to dN is equal to t d theta, and combining the equation 3 and 5 is over here and the 3 equation is over here. So, if you combine these two, then I have dt by t is equal to mu s times d theta, that is the change in tension over the tension at that point is equal to mu s times the angle over which this change is taking place. And then if we integrate it from end to end, that is from the contact point, let us say from this point to this point. So, over the entire angle of wrap, okay. And at that point, at this point the tension is T2, at this point tension is T1. So, it means integral dt by t from T2 to T1, and correspondingly d theta is varying from 0 to beta, the total angle of wrap, and mu s being constant, that is the surface is same surface of the pulley and the same drum. So, mu s will be same. So, mu s can be taken out. So, this integral is very simple. This will give me natural logarithm of T1 over T2, okay. And since d theta can be very easily integrated, and that is theta. So, in the limits it will be simply beta. So, this will be beta times mu s, s is in subscript. Well, if I take the exponential on both sides, log, natural log and exponential, they will cancel. So, T1 over T2 is equal to e to power mu s times beta. Okay. Therefore, at the moment of impending slip, that is when the slip is just about to take place, the ratio of two tensions depend on the angle of wrap beta and the coefficient of static friction mu s. Well, that was the case when the slip is just about to take place. Let us say when the slip has already taken place, there is this, that is the belt is sliding over the drum or the pulley, then the coefficient of friction mu s will be replaced by mu d, coefficient of dynamic friction. Rest is expression is same, that is T1 over T2 will be equal to exponential of mu d times angle of wrap beta. Now, the torque transmitted by the system, well, there is a force T1, there is a force T2, both are acting at the points tangentially. So, the distance from the center is radius r here, radius r over here. So, there will be a clockwise torque T1 into r, there will be anti-clockwise torque T2 into r. So, the net torque will be T1 into r minus T2 into r. So, the net torque will be r times T1 minus T2. Now, look here, we have found out the, let us say, tension T1 and T2. If I look at the entire system, that is this pulley which is mounted on some axle or a shaft through some bearings, and the pulley is rotating over which the belt is going with these two tensions. Let us try to examine the equilibrium of this pulley or the drum. There is a self weight W of the drum WD, and then there are two tensions in the belt which are, since the belt is wrapped on the drum. So, these forces are essentially acting on the drum. So, there is a force T1 and T2. These two forces can be resolved into two components. Let us say the angle of inclination of the this part of the belt to the horizontal is alpha 1, lower part of the belt to the horizontal is alpha 2. So, T1 cosine alpha 1 plus T2 cosine alpha 2. These are the horizontal component of the belt forces on the drum. These have to be resisted by the reaction from the bearings, which will ultimately be transmitted to the axle of the pulley. Okay. So, this force reaction from the bearings F is equal to T1, this horizontal reaction, T1 cosine alpha 1 plus T2 cosine alpha 2. Now, what about the vertical balance of forces? Again, downward force is WD downward, and then T1 is, you can again resolve horizontal and vertical downward. Similarly, this will be vertically upward. So, the net vertical force which is to be resisted is Wd plus T1 sin alpha 1 minus T2 sin alpha 2, and this will also come from the reaction of the bearings. So, it means that the pulley is in equilibrium or is being maintained in equilibrium by two reactions F and R. Now, this F reaction can be adjusted depending upon the requirements, that is tension T1 and T2. You might have seen that again taking example from automobiles, which many of you might have experienced yourself, that is when the belt becomes loose sometimes due to excessive usage, after it is a rubber or some synthetic material, then the mechanic will push the pulley a little bit so that the distance increases and the tension in the belt is adjusted. So, in that case the attempt is that the belt should not slip over the pulleys, it should move with the pulleys, no slipping, because once slipping takes place there will be lot of heat generated, the belt will deteriorate and it will ultimately break. So, in a proper operation of the belt pulley system, the force, horizontal force at the reactions or the horizontal reaction at the bearings should be always adjusted in such a way that there is no slip. Well, in today's lectures we have seen the application of friction in many situations. Some of them are very relevant to our daily experiences. I have given examples from the wheel climbing up a step. I have given examples of automobiles in which belts and pulleys are used. Again, in the industry or in a workshop, belts and pulleys are used. So, the phenomena of friction is very relevant to our daily experiences. We will continue with more application of this phenomena in our next lecture. So, thank you very much for your attention, and I hope you will be able to correlate whatever you have learnt today with your further experiences.